multiple angle identities. What we want to be able to do is understand and use the double angle identities. That's definitely an objective for today. Understand and use the power reducing identities a little bit. You know, we're not going to really get through everything we need for that today. Understand and use the half angle identities. We'll maybe touch on it today. And then solve trigonometric equations. Not at all today. We won't get there yet. There's so much packed into this section. And each problem is multiple steps. So we just have to kind of take it slow and follow along as best we can. And at any point I go too fast and something I do, you're like, wait a second, I was still thinking about this and I didn't catch what you did there. Stop me. Multiple steps for everything we're going to do today. And when you look at the formulas, you see why. You know, we've got the double angle formula for sine. Sine of 2u equals 2 sine u cosine u. In fact, we're going to prove that in just a minute. Cosine of 2u. We have 3 different formulas that we can use for that, and it's dependent on what information you have. For this first one, you know, if you can easily find the cosine of the angle and the sine of the angle, that's the best one to use. I mean, when you look at it, it even reminds you a lot of cosine squared plus sine squared equals 1. You know, it's not, but it reminds you of that. And then this would be if we're just dealing with the cosine of the angle, just dealing with the sine of the angle as information that they've given us. And then tangent of 2u, a little more involved because, you know, tangent is going to be sine over cosine. And so this is a formula that's derived from the other two as we go through that. So now, what we want to do first is make sure that these are always going to work. And if they're always going to work, they have to be provable. The problem is, you can't use the identity to prove itself. You have to use past identities to get there. So I've got sine of 2u equals 2 sine of u cosine u. And if you look up there, that's exactly what it said. That's what the sine of 2u is. But our thought process needs to be, okay, what have we done in the past that could give us the sine of 2u? Ideas. How about if I break it up? Is this 2u? Does that look familiar? Yeah. Now it's like, oh, wait a minute. We did angle addition before. We did that. Okay. So far we have the sine of 2u equals the sine of u plus u. Now let's deal with that. And we say to ourselves, sine had that nice pattern of sine, cosine, cosine, sine. Did we have to change the sign when we dealt with sine, the trig function? Nope. Plus, plus. And then it was always, hey, put the first one in for u and v, u and v. Well, they're both u's. Sine of u, cosine of u, plus cosine of u, sine of u. Well, they're backwards. And I think everybody knows multiplication is going to be commutative, so it doesn't matter that we have sine first or cosine first. But if we wanted an intermediate step, now would be the time where we would say, okay, I'm going to reverse this one so that everybody can see, yes, they're exactly the same thing. And if I have one of them and I add one more, now I have 2. So that's the matter of just a few steps to get to that. In fact, it was one of the things that you proved in the homework in the prior sections was sine of 2u. But they gave it to you like that instead so that you can see it. So we know it works. It's a matter of now, okay, once it works, then use it. Figure out what's going on. So this one gives us cosine x equals negative 2/3. And sine of x is greater than 0. And I'm going to stop right there because we've done that before. I mean, we've had, hey, here's what one of the trig functions is. Here's which quadrant you need to be in. And I'm going to see what I have. So think about my quadrants. Plus, 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 minus, 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 plus, minus, plus, minus. And I need a quadrant where cosine will be negative, but sine is positive. Where do we go? Quadrant 2? Okay, let's get our triangle on there. Cosine x is negative 2/3. Cosine is adjacent over hypotenuse. And I wrote 3 for a 2. So hypotenuse would be 3. Now I look at what they want, and I see they want us to find double angle identities, cosine, sine, and 2x. And I realize that the formulas that I have up there require that I know something about cosine and sine. So one of the places to go right away would be, well, let's figure out what this other side is. I mean, we could do that. That's a little Pythagorean theorem stuff here. So negative 2 squared plus b squared equals 3 squared. 4 plus b squared equals 9. B squared equals 5. B is the square root of 5. And it is positive because it's going up. Here's the problem. They don't want that triangle. They want the ones that are twice as big. So I have to figure out which quadrant my twice as big angles are going to end up in. So I start with this, and I say to myself, self, this angle was between pi over 2 and pi. That's what it was between. But that's not the angle they want. They want twice as big as that. So what I need to do is multiply this by 2 to see where it could possibly land, where that angle will be when it lands. So let's see. 2 times pi over 2 would give me pi less than 2x less than 2 pi. Oh, well, that wasn't real helpful. Of course it's going to land down here somewhere. I just want to know where. But at least it gives us the general somewhere down here. So as we're working through it, we can think about, are our signs matching quadrant 3 or are they matching quadrant 4? Because this is not a special triangle. We can see that. So we don't know. My sketch is not accurate. I don't know. Is it closer to the y-axis here? Is it closer to the x-axis? So I'm going to use what I have with the math to tell me which quadrant this is going to end up in. So now, we start with cosine of 2x. And we take a peek back up at the formulas. And we say to ourselves, self, what can I use here? Well, actually, we could use any 3 at this point, but I want to start with the cosine squared u minus sine squared u for you. And ours has an x in it, so we're going to go ahead and use the x's. Oops, I reversed it. Okay, so there's our little formula. The good news is we have our triangle drawn. We absolutely can find those things. We know what the cosine, because remember, it looks like cosine squared x, but what it really means is cosine x squared. That's what it means. And we have a triangle up here set up so that we can find cosine and sine. In fact, they gave us cosine. Cosine was negative 2/3. Sine, because we took the time to find that third side for our triangle, we can say, hey, opposite over hypotenuse. That's math we can do. Remember, you can distribute that power of 2 into the parentheses when it's pure multiplication or division. There's no addition or subtraction in there. We can distribute this. So negative 2 squared will be 4, and 3 squared will be 9. The square root of 5 squared is 5, and 3 squared is 9. 4 ninths minus 5 ninths. Negative 1 ninth. Is that enough to tell us which quadrant this is in? Where would our double angle have to be at if we just did the cosine and it came out negative? It has to be quadrant 3. So we're going to use that if in the future we need to know whether or not something should be positive or negative. We're going to look at this and say, okay, got to be in quadrant 3. Has to be. We just got a negative cosine. Has to be there. Next up, sine of 2x. We need a formula. Well, there's only one up there. 2 sine of x cosine x. Good news. We already know what sine of x and cosine. We just used them in the last one. So we'll have 2 times sine of x, square root of 5 over 3. Cosine of x, negative 2/3. Or,
Why does it have to be in quadrant 3?
oh, we just did the cosine of our double angle, and it came out negative. Remember, from what we had in this inequality,
Okay.
we said it had to be somewhere in quadrants 3 or 4, from pi to 2 pi. So we just absolutely narrowed it down now. We absolutely know that that's where it is. It was only here or here that it could be that double angle. Alrighty, so we keep going with this. And we see we have a negative 4 square roots of 5 on the top. And again, fractions, it's always, bless you, top times top, bottom times bottom. So negative 4 square roots of 5 over 9. Perfect answer. You know, we don't have a radical in the denominator. We don't need to rationalize. We don't need to do any of that.
Why doesn't the x ever get squared?
Oh, because even though it looks like this is what it means.
Yeah, why does
So once we find that cosine, we use that numerical value and then we square. Yeah, it's just kind of the language of trig. Alrighty, next up. Tangent. Well, we only get one formula for that. 2 tangent x over 1 minus tangent squared x. There. Well, we better go back to our drawing and find out what tangent of x was, huh? Opposite over adjacent. Square root of 5 over negative 2. Negative square root of 5 over 2. So let's plop it in, see what happens. Well, kind of good stuff in our numerator. You know, the 2's are going to cancel out there and we'll get negative square root of 5. A little more work in the denominator. Negative square root of 5 squared is just going to be 5. 2 squared is 4. 1 minus 5/4. That's 4/4 minus 5/4. Which is a negative 1/4. And then we're going to have to multiply by the reciprocal. So negative square root of 5 over 1 times negative 4 over 1. Which gives us a not so awful 4 square roots of 5. Now that we've used the formula, what would have been another way that we could have found tangent? Sine of 2x over cosine of 2x, exactly. But in your homework, you're not always given, so you don't always do all 3 of them. So I wanted to make sure everybody knows you can use this formula standalone to get just the tangent of that double angle, that 2x. Okay, everybody all right with that one? And let's move on. Power reducing identities. Sine squared u, 1 minus cosine 2u over 2. Using the double angles, that's what it does. Cosine squared u, 1 plus cosine 2u over 2. Again, some of these we accidentally proved in the other sections and didn't know we were proving them. And then tangent squared, 1 minus cosine 2u over 1 plus cosine 2u. Some books, just so you know, some books will give you these, bless you, like this. There are circumstances where it's easier to work with the problem if the fraction is out in front. But most of the time, I actually prefer it in this fraction form until we get to the point where it definitely becomes necessary to pull fractions out and take a peek at them. So first thing we need to do to make sure it works is prove that cosine to the fourth of theta minus sine to the fourth of theta equals cosine of 2u. And we're going to see pieces of everything that we need as we go through here. So start with the more complicated side. And hopefully when you looked at this you thought, ooh, that's factorable. So we would get cosine squared theta plus sine squared theta times cosine squared theta minus sine squared theta. If for one of those, the bells should go off in your head. Ding, 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 ding. That's a good thing. Which one?
The first one.
First one is what? 1. Excellent. This is one of those proofs where it helps to think backwards, so you know where you need to go. So I go up here, and I think to myself, well, I can't use the double angle identity to prove the double angle identity, so I'm going to go back to this, right there, cosine of theta plus theta. And what we did before, which was, okay, for cosine, that's going to be cosine, cosine, sine, sine. With cosine, do we need to change the plus to a minus? We do. Wait a minute. Isn't that what we have? So we know where it has to hook up, and right now what we should do is write this like this. Cosine theta minus sine theta, because that sets us up for cosine theta plus theta, which is something we already learned, already proved, and brings us back to theta. So, left side, more complicated. Start by factoring, get to a point where you're like, wait a minute, where is this going again? Somehow I'm supposed to get this. Break it apart. This is what I know from the past. Hey, look at that, it hooks up. And we have our proof. Now, we know that works. What we want to do is try to figure out how to use it. Yep, Wayne.
Why don't you go from the second line right there? That one, yeah. How'd you go from that to the next one?
Because this is really cosine theta squared. Again, what we do in trig is we put the 2 here so people don't get confused, but sometimes it actually makes it confusing when you go to do the proof. So cosine theta squared is cosine theta times cosine theta. That's what it is. And this would be its definition, actually, for cosine theta squared. It would. How? If you're going to use the double angle, yes. If you're going to be using those double angle identities, yes, we will.
How did the sign just?
Oh, because Remember this formula that we learned in those last three sections said, if you need this, you do cosine, cosine, sine, sine, but you change the sign in between those two angles. So this really is this. It's just kind of a backward thinking step of, wait a minute, this is what I saw in that formula. This is what it is. I'm working backwards. Okay, anything else before we move past that? Now we want to use them. Rewrite cosine to the fourth x in terms of trigonometric functions with no power greater than 1. Oh my goodness, it's a fourth power. And we're going to write this with no power greater than 1. We will. So let's see. I don't see any formulas up there for power reducing that have 4's in them. How could we rewrite a fourth power as something using squareds? Hey, isn't it squared of a squared would give you fourth power? Is that still fourth power cosine? Good. So we found a way around it. All right, now we need the formula for power reducing cosine squared. That's that middle one up there. 1 plus cosine 2u over 2. We're substituting the formula from up at the top of the page. 1 plus cosine, oops, I forgot a 2 there. 2x over 2. Put my x in the wrong spot, is what I did. That's better. We have to still work with the fourth power. This is just replacing cosine squared x because that's what the formula gives us. And now we have to square it so we keep that fourth power. Can't lose the fourth power.
Since it's asking us to just rewrite it with no power greater than 1, can we just write cosine x 4 times times each other?
You're going to see that it's much easier to do it this way. Not that this is an easy process, but this is much easier than going after it with 4 of them. It is. Okay? All right. So we need that squared. Remember, powers go to the closest thing to their left. So this is saying take this monster, write it down twice, and see what you get. Let's take that monster, write it down twice. Let's see what we get. Numerator times numerator, denominator times denominator with any fraction. Gonna do a little FOIL action up there on the top. 1 plus cosine 2x plus another cosine 2x. Unfortunately, last time's last. Cosine squared 2x. Now that's a problem for us because they said we have to have this as a first power, but we're not going to deal with it right now. All over 4. Is the entire problem something squared? Is every term that you see up there something squared? No. So what we want to do is separate it out. Remember before I said sometimes it's better to separate out the fractions? This is the now. We've got a 1/4, 2/4 cosine 2x, and 1/4 cosine squared 2x. These terms are not the issue. That one is. That one still has a squared. And the instruction said, rewrite cosine to the fourth of x in terms of trigonometric functions with no power greater than 1. So we're not done. But we already know what to substitute in. for cosine squared 2x. So we need to substitute one more time. 1/4 plus 1/2 cosine of 2x plus 1/4. We have the formula. 1 plus cosine 2x over 2. Looks like that. Except we just put a 2x into a formula that already had a 2 in it. So that's not 2x anymore. That's a 4x. Before, when we were just putting an x in it, we could just get 2x back. But now, that says 2x. So 2 of the 2x's would be 4x. Well, let's see what we have. Still have to distribute that 1/4. So 1/4 plus 1/2 cosine of 2x equals, multiply top times top, bottom times bottom, not equals, for goodness sake, plus. 1 plus cosine 4x, but this will all be over 8. And then I think, well, am I done? Have I simplified as far as I can? And I realize the answer to that is no. And that's because this 1/8 can be split up from this cosine of 4x over 8. And then I can put a couple of fractions together. So 1/4 plus 1/2 cosine of 2x plus 1/8 plus cosine of 4x. And actually, let's make it 1/8 cosine of 4x since we're putting all the fractions out front end. Does everybody see we have a couple of fractions we can put together now? We have the 1/4 and the 1/8. Because both of these things have the 8 underneath them. Both of those terms. And thinking backwards, take a look, Holly, how these would both have the same denominator. So we could put them back together and it would be 1 plus 1 cosine of 4x over 8. So it has to work forwards and backwards as you go through the process. Both of them have an 8 under them. So when we split them up, they both need an 8 under them. All right. Might be helpful at this point to have everything in 8s, since that seems to be our least common denominator. So let's see what we have in 8s. 2/8 plus 4/8 cosine of 2x plus 1/8 plus 1/8 cosine of 4x. Well, 2/8 plus 1/8 is 3/8 plus 4/8 cosine 2x plus 1/8 cosine 4x. And this last step is something most mathematicians will do to just clean it up and make it look a little nicer. And that is factor the 1/8 out of the whole thing, so you don't have fractions in each and every piece. 3 plus 4 cosine 2x plus cosine 4x. It's done. Good.
How would you use this in real life?
You may never use that in real life. But the thing that you're going to use is every business person, really you could blame a lot of what we do in math on business people. Every business person that ever talks to a college or high school says, we need people that can take complex problems and break them down into steps. Perfect fit. Complex problems where we break things down into steps. You know, that's the thinking they want everybody to have. A long time ago, in fact, I went and listened to testimony at the state about the state standards that we have right now. Everybody that was in business up there was saying, We need more people that can come out of high school taking big complex problems, breaking them down into little steps, every single one of them. So that's where a lot of this comes from. Other than rocket science, I'm not really sure. All right, so still have some time here. Alrighty, look at that one. Express sine squared x cosine squared x in terms of a single power of cosine. It'd be very similar to what we just did. Very similar. So, grab your green sheet and say, okay, I need sine squared x and cosine squared x.
Okay, I have a question referring back to like how it like relates to real life. Are they using like math problems in business that you're seeing, or just like real life situations where it's
These are complex thinking problems that have to be broken down into steps. And that's exactly what they want.
So we're breaking down just like real life problems in the real world into steps, not math problems.
It's the thinking steps that would be exactly the same. Exactly the same.
Okay.
Because that's how the brain works. It doesn't matter if it's math. It doesn't matter if it's figuring out which route would be best as a best for a trucker to take to save on gasoline. I mean, it's all math. It really is.
Okay.
So the complex steps that we use, those are the steps. Alrighty, looks like that. We've got 1 minus cosine 2u, or 2x in this case, and 1 plus cosine 2x, both of them over 2. So let's see what happens when we multiply these two monsters together. Foil on the top. I'm going to need a little more space. 1 times 1 plus cosine 2x minus cosine 2x, middle term is gone, minus cosine squared 2x over 4. Problem. Single power of cosine. Yes?
If when we do this step, we just simplify cosine squared 2x, just like put it in parentheses, or do we just leave it like that?
We have to put it back in the formula again. And that's because this is still a double angle. This is still a double angle. So we have to put it back in. So we want to separate these two because we're still going to have to put something back in the formula. So this is going to be 1/4 minus 1/4 cosine squared 2x. So now we're at the spot we were in the last one. While we got rid of squared times squared being kind of 4th power, even though they're not the same base here, we still have a cosine squared 2x we need to eliminate. And that means we're going to use the formula again. So 1/4 minus 1/4. And let's slap in what we know for cosine squared 2x. And we are not ever taking these formulas away from you. That's why I gave you the green sheet, so that you can constantly reference that and pull them over here. Even mathematicians will look these up before they use them. It's just not something most people will memorize as we go through these steps. So we've got our cosine squared 2x again, which is 1 plus cosine, but we just put 2x into a formula that already had a 2 again. So 1 plus cosine 4x over 2. Well, let's distribute our nice little negative 1/4 there and see what happens. So we'll get negative and negative here. Negative 1/8 minus 1/8 cosine 4x. A little bit to put together, right? Got 1/4 minus 1/8. Well, 1/4. 2/8, 2/8 minus 1/8, 1/8 minus 1/8 cosine 4x. This one, you'll find mathematicians that'll leave it just like that because there's two terms, but you'll also find some that will pull that 1/8 out again.
Which way do you want us to?
I'll take it either way. I really do like this way. I mean, in terms of looking simpler, this looks simpler, but I would take it this way as well. How?
1/4 in front of the 1/8 right there.
1/4 is
Okay,
2/8. 2/8 minus 1/8 is 1/8. And we still had the last term. Okay, Holly. now I think I can-
Oh, yeah.
That was what it was? Okay.
What happened to these formulas on that test?
Oh, you're given all of them. The only ones you have to memorize are the ones you already memorized. You know, those are it. Every one of these formulas you'll be given. Yeah. And they'll look exactly like this so that there's no, hey, there's a plus or minus thing sticking in this one that we didn't see before. You know, it's gonna be just like this. All right. Good news, we have time to talk half angle identities. We do.
don't.
Our little box here says, aren't we forgetting that all of these things could be plus or minus? And it says you might have noticed that all of the half angle identities have unresolved plus or minus when you look at all these formulas down here, except for the last two. The fact that we can omit them on the last two identities for the tangent is because it's a fortunate consequence of two facts. And that is sine of x and tangent of x over 2 will always have the same sign. Wherever tangent is positive, sine is positive. And wherever tangent or sine is negative, tangent will be negative. And it says it's easily observed from the graphs of the two functions in figure 5.10. Well, it's also easily observed if you just punch it into your calculator. You see that wherever sine is above the x-axis, tangent of x over 2 is also above the x-axis. And like it says, in the last one, 1 plus or minus cosine u will never be negative, never negative. And that's because if we have this 1, remember that's going to be a vertical shift. And so we're moving that graph up. It's never going to pass the x-axis when we do that. So if you don't want to look at figure 5.10, last night I very quickly graphed these graphs on my graphing calculator. Very easy to see what it was they were talking about. And if we have time on Monday, I might start with that. I'll leave something. So now, look at those marvelous formulas right there. Don't they look like fun? They're actually not as bad as all that. I mean, they look horrendous. There are going to be times when we are going to have a radical embedded in a radical, which we can't leave. So we're going to learn how to deal with radicals inside radicals as we work with these half angle identities. But the rest of this math that goes into this it's not awful. It isn't. It's not awful. So it says find the exact value of the sine of pi over 8, which we would say can't do it. There's an 8 in the denominator. We need a 3, a 6, a 4, or we need that to be quadrantal somehow. But if you take pi over 4 and you divide it by 2, you will get pi over 8. So we can find this angle exact. And that's what this is about, finding as many of these as exact as we possibly can. So we want the sine of pi over 8 divided by 2, pi over 4 divided by 2, so we can get pi over 8. Right there. So, things to think about. Again, we need to be thinking quadrants as we go through this. So even though I know everybody has memorized the sine of pi over 4 by this point, what you might want to do is make yourself a little quadrant sketch again. Make it extremely visual, what you're doing. So our sine of pi over 4 would be obviously right there. A little 1, 1. Square root of 2, or 45, 45, 90. And we need to know where's pi over 8 going to go. Well, it's pretty obvious, cutting that angle in half, it's gonna stay in first quadrant. So Cedar Home, why did you do this? Because we don't always get a nice first quadrant angle. So if it's not a first quadrant angle, then we have to figure out, okay, where is this gonna land? And we do the same thing we did with double angles, where we say, right now, this is between 0 and pi over 2. What's going to happen to it if we split it in half? We will be in quadrant 1. We will definitely be in quadrant 1. But like I said, on later problems, they're not all quadrant 1, so we still need to go through that step. So now, what are we going to do? We're going to plot this in our little formula up above. So we need the sign for pi over 4 over 2, which they had as u over 2. We'll do x over 2 there. And that's going to be plus or minus the square root of 1 minus cosine u over 2. I'm just going to put an x in there instead. Oh, because this is the half angle identities. We want to know if you cut these angles in half, where they're going to land. Yeah. You could also divide everything by 2. It'll give you the same stuff. All right. So now, I want pi over 4 over 2. So what I need to do is use the cosine of pi over 4 in this formula. And again, you probably already have it memorized, but know that later on it might be helpful to have a little sketch. And that'll just remind you, 1 over the square root of 2. Oh, wait a minute, it's the square root of 2 over 2. Now we're going to plot that in this formula. We're going to drop the plus or minus because we already know that our half angle has to be in first quadrant. We don't need the negative anymore. And I know it's kind of, when you look at your notes later, it's going to be kind of, where did the plus or minus go? Well, it went to the fact that we know this angle is going to be in quadrant 1. So we don't need that anymore. So 1 minus the square root of 2 over 2 divided by 2. Fractions within radicals. Now that's fun. So now what do we do? Well, we're going to get a common denominator for the numerator. So we have one fraction up there. And then we'll be able to multiply by the reciprocal. And we'll see what we get. So, square root of, well, 1 is 1 over 1, so we'd have to multiply the top and the bottom by 2 and get 2 over 2 minus the square root of 2 over 2, all divided by 2. So we have a common denominator, 2 minus the square root of 2 divided by 2. And we have to divide that by 2. Well, that's not a big deal. All we're going to do is multiply it by 1/2. Okay, top times top. Bottom times bottom. We're not allowed to leave radicals in the denominator. Remember, this is an exact answer, so we are going to rationalize the denominator, but good news. When we split this up, the square root of 4 is just 2. That's an embedded radical right there. We have a radical within a radical. And that is a perfect answer. Beautiful. Again, some professors pull a fraction outside. But either way, beautiful answer. Perfect. Perfection. Love that in math. Anytime we can get something perfect. Anything about that one? Okay, feeling a little more comfortable with the formulas?
Do we always want to take the 1 line off the bottom? Every time?
Yes. Yes. We do. Hey, there was another one in this problem.
We gotta go.
I got it.
Yeah,
We do. Not gonna be able to do them all. What a bummer.
That's the last time.
It is formulas, everybody sees that, right? I mean, they're not easy formulas, but it is formulas. So if you're a formula person and just keep your head about you and just keep simplifying, everything will be okay.